The architecture of interplanetary communication represents one of the most sophisticated applications of Maxwell's electromagnetic theory, serving as the sole umbilical cord between Earth and its robotic emissaries across the solar system. At its fundamental level, space communication is the art of extracting meaningful data from background cosmic noise across vast vacuum distances where signal degradation follows the uncompromising inverse square law. This process begins with the conversion of digital telemetry, binary sequences representing everything from engine temperature to high-resolution spectrographic imagery, into modulated radio frequency RF waves. Because the vacuum of space offers no atmospheric interference, these waves travel at the terrestrial constant of light speed, approximately 299,792 km per second. However, even at this ultimate velocity, the sheer scale of the cosmos introduces a physical constraint known as propagation delay. For a mission to Neptune or the Kuiper Belt, a single command can take over 4 hours to arrive, necessitating a high degree of onboard autonomous processing and fault protection logic, as real-time joystick control is physically impossible. To ensure data integrity over these distances, engineers employ advanced forward error correction (FEC) techniques. Algorithms such as Reed-Solomon and low-density parity check (LDPC) codes add redundant parity bits to the data stream. This allows the receiver on Earth to mathematically reconstruct missing or corrupted packets caused by solar radiation interference or galactic cosmic rays. Once the data is encoded, it is transmitted via specialized frequency bands. While near-Earth missions often utilize S-band frequencies for their reliability, deep space missions migrate toward X-band and Ka-band. These higher frequencies allow for narrower beam widths and higher data throughput, though they require extreme pointing accuracy, comparable to hitting a moving coin with a laser pointer from several kilometers away. The infrastructure supporting this dialogue is the Deep Space Network (DSN), a global tripod of massive antenna complexes situated in Goldstone, California, Madrid, Spain, and Canberra, Australia. By spacing these facilities approximately 120 degrees apart in longitude, at least one station always has a direct line of sight to any given spacecraft as the Earth rotates. Each site houses gargantuan 70-meter parabolic reflectors, capable of capturing signals so faint that they possess less energy than the snowflake hitting the ground. To distinguish these signals from the thermal noise of the electronics themselves, the feed horns of these antennas are often submerged in liquid helium to reach cryogenic temperatures, minimizing molecular agitation. Orbital mechanics introduce further complexity through the Doppler effect. As a spacecraft moves toward or away from Earth at tens of thousands of kilometers per hour, the frequency of its signal shifts. Ground stations must constantly tune their receivers to account for this compression or expansion of waves. This phenomenon is not merely a challenge but a tool. By measuring the precise frequency shift, navigators can calculate the spacecraft's velocity and position with sub-centimeter precision, a process vital for gravity-assist maneuvers and planetary insertions. For spacecraft in low Earth orbit (LEO) that lack constant ground station visibility, the space network provides a relay solution. Using a constellation of tracking and data relay satellites (TDRS) in geostationary orbit, LEO satellites can look up to bounce their data down to a single ground terminal. This eliminates the blind spots that famously plagued the early Mercury and Gemini missions, where astronauts were out of contact for the majority of each orbit. As we transition into an era of Mars colonization and high-definition lunar exploration, the RF spectrum is reaching its Shannon-Hartley limit, the theoretical maximum rate at which information can be transmitted over a specific bandwidth. The solution lies in optical communications or lasercom. By using infrared lasers instead of radio waves, we can increase data rates by a factor of 10 to 100. Because laser wavelengths are significantly shorter, the energy is packed into a much tighter beam, allowing for smaller, lighter equipment on the spacecraft. However, unlike radio waves, lasers cannot penetrate thick cloud cover, requiring a sophisticated network of ground sites in arid regions or space-based optical relays. In conclusion, the evolution of space communication from the primitive beeps of the mid-20th century to the gigabit-scale laser links of the 21st century is a testament to human ingenuity. It is a discipline that marries the abstract beauty of information theory with the brutal realities of orbital physics.